Hi everyone, welcome to day 2, or I guess day 3 of Calculus 2. So today we are covering chapters 6.3 and 6.4. So the first one is chapter 6.3, which covers volume by slicing. Got my pen, there we go. Okay, so this is kind of an extension of what we were talking about the last class, right? Last class we were talking about how to find areas of different shapes. This class will be specifically talking about how to find volumes of different shapes. So we are going to be looking at very specific three-dimensional shapes, specifically what are called solids of rotation, or solids of revolution, excuse me, solids of revolution. These are basically formed if you take something and rotate it around something else. So this would happen if you were to say, take your object, you cut it down the middle, you're going to have a circle shape as the inside. And I have a picture here that's pretty good at explaining what these things look like. So in this picture here, what you're doing is you're seeing we're taking this shape right here, given by the curve f of x, and we're just going to rotate it around the x-axis in order to get our final three-dimensional shape. And these are going to be the types of volumes that we're going to try to find. In general, you can actually find basically volumes of any three-dimensional shape using a very similar technique. You'll cover that in Calc 3 if all of you go on to take Calc 3. So that will be more general shapes. We'll just be talking about these very specific solids of revolution where these cross sections are going to be circles. Great. So let me grab another picture right here. And talk about how we are going to do this. So the basic idea, right, is that if we're given some function f of x, we know what the radius is at any one specific point, right? We know that the radius is just going to be this f of x, right? And you can see this from this figure 6.29 down here, f of x. So what that means is that if we were to slice it into different pieces and we were to just look at the area of the circle, which is always given by a of x, is just going to be the area of a circle, so pi r squared, which we know is going to be f of x squared times pi. And now what we want to do, right, is we want to take all of these different areas, add them up, to get us a volume. This is very similar to the Riemann integration you all would have talked about in Calculus 1, where we have some curve here, right? And we looked at these small rectangles, and then we took smaller and smaller rectangles, right? And then that would eventually lead us to the integral in order to figure out this area here. This will be a very similar process, and we're actually going to have a formula where the volume is going to just be the integral from a to b, where a is the left x value, b is the right x value, so in figure 6.9, this is going to be my a, which is going to be 0, and my b will be right here, which is not given to us. So right x value and left x value, and all we're going to do is we're just going to take all of these different areas and integrate over them. So pi f of x squared dx. Okay, so let's just go straight into an example of how you'd actually go about solving this. So let me grab another picture here. Since I can definitely not draw in 3 dimensions, there'll be lots of pictures in this lecture. Okay. So say we're trying to find the solid of revolution around this x squared plus 1 right here. So it kind of forms this cone that's growing like a parabola, and we would like to know the volume of this. So what we want to figure out, we need to know what our a is, we need to know what our b is, and we need to know what our f of x is. So a is going to be our leftmost point. So we know that just from this picture right here, we're going to have a as 0. You can also see from this picture, right, our rightmost point is going to be 2. So b is going to be 2. And f of x is going to be x plus 1 squared. Right, and so now we can take all of these pieces, plug them into our integral, and solve this in order to actually get our volume. So we know our volume is going to be the integral from 0 to 2 of pi x plus 1 squared all squared. So if we do this, taking a squared, raising it to a squared will leave us with a fourth power. So this is the integral from 0 to 2 of pi x plus 1 to the fourth dx. Now what you could do in this case is you could fully expand out this x plus 1 to the fourth. You would get 5 different terms. You could integrate all of those like you normally would. Or what we could do is we could use u substitution with u equals x plus 1 in order to just get an integral of u to the fourth, which will be slightly easier to solve. So let's do that. It's also a good refresher of how to do u substitution. Right, so the u is always going to be the inside part, so I have u equals x plus 1. If I integrate both sides, I will get du equals, well, if I take the derivative of both sides, excuse me. If I take the derivative of both sides, I get du equals, well, the derivative of x is just dx, so du equals dx. My bounds are also going to change, right? I started with x equals 0, which if I plug this into this top equation right here, this u equals x plus 1, is going to give me that my lower bound will now become 1. And finally, my x equals 2 for my b value will give me that u is equal to 3. So doing all of these substitutions, plugging them into my integral, I know that this will actually be the integral from 1 to 3 of pi u to the fourth du. So the x plus 1 becomes u, dx becomes du from this, and I also have to change my bounds. Right, so integral of u to the fourth is 1/5 u to the fifth, so this is 1/5 pi u to the fifth evaluated from 1 to 3. And if you plug all this in, plug in the 3 to the fifth, will give me 243 pi over 5 minus just plugging in 1 will just give me pi over 5. And so my total area is going to be 242 pi all over 5. And we'll just say it's units cubed. All right, so yeah, this is just the volume of this shape here. And you can see that this would come into play often in basically any type of field where you would need to be measuring volumes. This would be particularly helpful. So this is used a lot of times in real-world applications as well. Great, so we are going to talk about a couple of different ways that we can do this. So the next one we're going to talk about is instead of revolving around the x-axis, what do you do if you want to revolve around the y-axis? So revolving around y-axis. Okay, so I have another problem for this as well, which is this one. Great, so if we have the function y equals cosine to the negative first of x, and I would like to revolve this around the y-axis in just kind of the shape that makes sense, where I'm going from 0 to pi over 2. I would like to figure out what the area of this is going to be. So the big changes in this, and there's just going to be 2 of them, and they're actually the exact same as they were in chapter 6.2. So a, b are now y values. Now y values. And we need to make sure that our function is in terms of y. Need f of y, not f of x. So in this case, it's already given to us that our function f of y is going to be cosine of y, right? I can just take cosine of both sides of this in order to get x equals cosine of y. We can also see from this, a is always going to be our bottom y value, our smallest y value. So a will be 0, and b is going to be pi over 2. And we're just going to use the exact same formula we used for the previous problem, where we have that our volume is the integral from a to b of pi f now of y squared dy. So plugging everything in, this is the integral from 0 to pi over 2 pi cosine squared y. The general strategy we use when we have, say, cosine squared is that we like to make it in terms of cosine instead of just cosine squared, because we know how to take integrals of cosine. So if you remember back from trigonometry, we have cosine squared of y equals 1 plus cosine 2x over 2. And this then, plugging this in for cosine squared, that should be a y. Plugging this in for cosine squared will allow us to actually do the integral, right? Because we know how to take integrals of every single part of this, where we don't necessarily know how to take the integral of cosine squared. So just using this substitution, this is the integral from 0 to pi over 2 of pi over 2 plus sine of 2y, or sorry, cosine of 2y, excuse me, cosine of 2y times pi over 2 dy. Okay, so we have 2 different things we need to figure out the integrals of. We need to figure out the integrals of pi over 2, which will just be pi over 2y, and we also need to figure out the integral of cosine of 2y. For the integral of cosine of 2y, we can just use u substitution again. Using again, u will be the inside part, so we will use u equals 2y. So u equals 2y. If we take derivatives of both sides, this means that du is going to be equal to 2 dy. And now we can plug everything in. So if we are trying to figure out the integral of cosine 2y dy, we just need to be very careful again to not forget about the pi over 2 there. I won't include it in the integral, we'll just include it at the end. Okay, so the integral of cosine of 2y dy, using our u substitution, we know that this now becomes cosine of u. Dy is going to become du over 2. So du over 2. This is now the integral of 1/2 cosine of u. Integral of cosine is sine, so this is 1/2 sine of u. So combining all of this together, we have that this integral here is going to be pi over 2 times y plus 1/2 sine of 2y, because that's what u is going to be, times pi over 2. And this is evaluated from 0 to pi over 2. The same bounds as we had for our integral. 0 to pi over 2. Okay, and we can plug this in. We're going to get that this is equal to pi over 2 squared plus pi over 4 times the sine of pi, and then minus everything that happens when we plug in 0. So the first part will be 0, and the second part will be pi over 4 sine of 0. Nice thing about sine of pi and sine of 0 is that they're both 0. So that's 0, and that is 0. So we are just left with pi squared over 4 as our final answer. So this kind of funny looking cone shape right there is going to have an area of pi squared over 4 units cubed. Add that in, units cubed. Okay. So the other thing that we can do is we can revolve around axes that aren't going to be the x-axis or aren't going to be the y-axis. So I have another picture for this as well. This is 45 from the textbook. Say that we have this region here, so it's the region bounded by those 3 curves, and instead of revolving around the x-axis, we want to instead revolve around the line y equals 1. And you can kind of visualize what this will look like, right? We are going to get kind of these circles, and it will look like this. Okay, so this is the volume that we are trying to find. And if we go back to how we originally talked about this problem, right? We talked about this area of x, where this is going to be the area of some cross-section at x, is f of x squared times pi. And the reason this worked is this f of x was the radius. However, now this is going to change, right? The distance I am away from the x-axis is no longer going to be my radius. Instead, I want to know how far I am away from the center line, and this center line is going to be y equals 1. So my radius in this, and you can actually kind of see it right here, is going to be 1 minus my function. So it'll be 1 minus the square root of x. And this is going to be my radius in this problem. So then we can do the same thing, right? We're going to integrate over all of these different areas, but now we have a changed radius instead of our original radius, and we can do it that way. So we note that this 1 minus 1 is going to cancel, and this is just left with the square root of x. So my integral now becomes 0 to 1, where 0 is my leftmost x value, 1 is my rightmost x value, of pi times the radius, square root of x squared dx. And this is not too bad to solve, right? Squared gets rid of a square root, so integral from 0 to 1 of pi times x dx. Integral of x is x squared over 2. So I have x squared over 2 pi evaluated from 0 to 1. The 0 will go away, so I'm just left with pi over 2 units cubed as my final answer. So the big difference in this is we just need to think about what the radius is going to be. So in general, we're going to do different things if I have horizontal lines versus vertical lines, right? So if I have a horizontal line, and let's just say it's y equals k. We haven't used the letter k yet. Y equals k. I'm just going to figure out my radius now as the distance from that line. So I will have the integral from a to b, where a and b still take on the same meaning, but now I have k minus f of x squared dx. And don't forget the pi as well. So this is just going to be the new radius. This, you can think of horizontal lines as similar to the x-axis, and so vertical lines will be similar to the y-axis. So vertical lines which are given by, erase that, x equals h, we'll say. This is now just going to be the integral from a to b of pi h minus, now only difference, we now have a function that's in terms of y instead of in terms of x. So f of y squared dy. And that's in general how you are going to solve these types of problems. So the third kind of extension of this that we're going to talk about is going to be what's called the washer method. Washer method. So a big idea behind this is that if you look at basically any shape that's around you, or a lot of shapes that are around you, they aren't necessarily all filled all of the way in. So we want to be able to know how to deal with things that aren't filled all the way in. Specifically, we're going to look at things that have cross sections that look like washers. So we want cross sections that look like this, where we have two circles and we only care about the outside part right here. So it's kind of hollowed out in the middle. It's called an annulus as well as a washer. So a picture of this that we have, which picture is it? This one right here. There we go. So this would be the type of shape you're looking at, where we have this kind of hollowed out inside part in our volume that we're trying to figure out the area of. Now, the nice thing about these cross sections is that we still know what the area of the cross section is. So if the inside circle has a radius of r1, the outside circle has a radius of r2, the area of this is just going to be r2 squared pi minus r1 squared pi. So we're going to take the area of the entire outer circle and then just subtract out that middle part. So we only have this middle part that we are actually caring about. So we can see from this that we actually can use the same method to get a general formula for this. So if I'm looking at this picture on the left right here, my area of any cross section is just going to be pi, and I will have f of x squared, so this is going to be my outer radius, and minus g of x squared. So in general, this is going to be the top function, and this will be the bottom function. So it's going to be whichever one will give a larger radius. And using this, I just do the same integration technique, and I'm going to get that my volume is equal to the integral from a to b, where a and b are my bounds on my x values of pi f of x squared minus g of x squared dx. Okay, so let's do an example of this. So the example that we are going to be doing, which I have right here, it's kind of this weird thimble shape where we're going to remove the cone from the inside of it. So we want to figure out what the area of this shape is. So if we look at this, well, my outer radius will always be this f of x, this x to the 1/3. So I have f of x equals x to the 1/3. My g of x will be the line, g of x equals x over 4. So what that means that I can plug things in, and my volume is going to be the integral from 0 to 8 of pi times x to the 2/3, right? That's just what x to the 1/3 squared is. When you take exponents of exponents, you always multiply, minus x squared over 16. Great, and this is something all of you should be able to take the integral of, right? It's just going to be exponents. So if we set this up, we're going to get that this is equal to pi, the integral of x to the 2/3 is going to be 2/5 x to the, 3/5 x to the 5/3, and then minus, we still have this pi here. Always make sure to distribute your pi through for these types of problems. The x squared will become an x cubed. We divide by 3, so we're going to get x cubed over 48. 48 is just 16 times 3, and we evaluate this from 0 to 8. And so if you actually solve all this out, do all of the annoying algebra, we're going to get that this is equal to 128 pi divided by 15. Okay, so this is how we solve these types of problems where we have two different curves and we have hollowed out regions that we are interested in. And the nice thing about this is it's almost a direct application from the other techniques we used to use them in the washer method. So to just give an example of that, I will go through one that uses the washer method, uses a different axis, and the axis is actually a vertical line instead of a horizontal line, and we will set up that integral. So problem, which we have right here, is going to be to figure out the volume of the solid rotated around the line x equals 2. So the interesting thing about this problem is that it's no longer going to be a solid, kind of like we were talking about before, right? There's this gap between the part from the actual region that we're rotating around and what we're rotating it around. So what's going to happen is that we're going to have this ring type shape, which is completely fine. The method still works on this. The cross sections, if you were to cut it in half, are still going to be circles. You're just going to have to be slicing it, make sure you're slicing it horizontally. But the method will still work for these ring type shapes. So if we think about this, right, we need an outside radius, and an inside radius, Well, the outside radius is just going to be this distance right here, which is shown really nicely in this picture. It's just the distance between the line x equals y minus 1 squared to this line x equals 2. One really nice thing to note about this problem is that we are already given the functions in terms of y instead of in terms of x. So you don't have to go through that additional step of solving for the functions that way. So my outer radius is going to be 2 minus 1 minus y minus 1 squared, and my inner radius will be 2 minus the square root of y minus 1. That's just going to be the distance between the center line. And so what that means is that our area of a cross section at a y value of y is going to be equal to pi times the outer radius squared, so it's 2 y minus 1 squared, and all of that is squared, subtracted from the inner radius squared. So 2 minus the square root of y minus 1, and all of this again is squared. We're not just squaring the functions, we are actually squaring this entire equation where we're subtracting 2 from the function. And so we can integrate this, and what we get is we get that this is the integral from 1 to 2 Very important to note, right? We're doing things in terms of y instead of in terms of x. So I'm looking at my y values as my integral bounds instead of my x values. So integral from 1 to 2 of pi 2 minus 1 minus y squared minus all of this squared dy. I forgot an extra parentheses. There we go. That was a bad parentheses. Okay. So what you can do is you can expand out all of these squared terms. Then it will be just a long list of different exponents, and you can take just integration of exponents in order to solve what this is. Which I am not going to do. If you would like an additional exercise, though, in figuring out what this is, I would recommend it. It's probably good practice, but a lot harder than something you would see on a test, especially since a lot of it is very tedious algebra instead of actual calculus. Great. Well, thank you all for listening. You've made it through 3 different lectures now. Again, if you have any questions, feel free to shoot me an email, come to office hours.